In this video, we're going to talk about some basic distribution functions that we're going to be using throughout the rest of the semester. The first is one you've seen a lot in your basic stats class, the normal distribution. We describe the normal distribution with the notation on the screen, which says that x is distributed normally, and that little tilde sign is translated as, is distributed as, and the n there indicates a normal distribution. So whenever you see this sort of notation, it means we're dealing with a variable with a normal distribution with a mean of mu sub x and a variance of sigma squared. So the first element in the function there is a mean, and the second is the variance. And as we noted earlier, the normal distribution is fully described by just those two parameters, the mean and the variance. The probability of any point on the normal distribution is 1 over the square root of 2 pi sigma squared e to the minus 1/2 x minus mu sub x over sigma quantity squared. And the normal distribution is that bell curve you've seen in so many basic stats classes as well as other classes. One of the reasons we use the normal distribution so often is the existence of a large variety of central limit theorems that all indicate that the distribution of many random variables tends towards a normal distribution as the number of observations rises. So for a wide variety of random variables, no matter what their underlying distribution, the sum of them will tend towards a normal distribution as we get to a larger sample. In particular, and this is what we're going to be using most often, the distribution of a sample mean converges to a normal distribution as the size of the sample approaches infinity, as long as the underlying distribution has a constant mean and a finite variance. Some properties of a normal distribution that we'll be coming back to quite often is that if x and y are normally distributed, the sum of x and y is normally distributed. Similarly, if we take a normally distributed random variable and we multiply it by a constant, a, then the variable a times x is normally distributed. Combining those concepts together, we get the property that any linear combination of normally distributed random variables will itself be a normally distributed random variable. What you probably worked with the most and what we'll be working with this week in class is what's referred to as a standard normal distribution. Since there's an infinite number of possible normal distributions over all the possible means and variances, we standardize this quite often for simplicity so we can use normal tables and standard normal distribution calculators. And we use a transformation z equals x minus mu over sigma. And what that does is it translates any normal distribution with a mean of mu and a standard deviation of sigma into one that has a mean of 0 and a variance of 1. And that's that standard normal table you work with so often back in your introductory stats class. We write that as the standard normal PDF is lowercase phi of z, and the standard normal CDF is capital Phi of z. As we noted earlier, if we have the PDF for something as f of z, the CDF will be capital F of z. And we're just following the same principle here with the Greek letters phi, where the lowercase phi is a PDF, the probability of observing any outcome, and the capital Phi is a CDF, which is a probability of observing any point less than or equal to the specific value we're measuring. So again, this is our standard normal variable, except the mean of it now is 0, and it has this particular shape where the variance is 1, which is also the standard deviation. Another distribution we'll be working with a lot is a ChiSquared distribution. And the ChiSquared distribution occurs when we take the sum of squares of n independent standard normal variables, and we end up with a ChiSquared distribution with n degrees of freedom. In other words, if we have any number of independent normal variables and we square them and add them together, we end up with a chi-squared distribution with degrees of freedom equal to the number of terms in that summation. We use that a lot when we're dealing with measures of the variance, and we'll come back to that very soon. What we can see, though, is if we have 2 degrees of freedom, it's a pretty highly skewed distribution. With 5, it's still pretty skewed, but it's starting to look a little more bell-shaped. Even when you get to a number as low as 15, it's starting to almost look like a normal distribution. It turns out in the limit, as n tends towards infinity, the chi-squared distribution will itself converge to a normal distribution. In general, if we take the sum of any two chi-squared random variates with m and n degrees of freedom respectively, the sum will follow a chi-squared distribution with m plus n degrees of freedom. The t-distribution is used in place of the normal distribution when we don't know the underlying variance. You notice the t variable that's listed here looks a lot like the z value, except instead of dividing by sigma, we're dividing by sigma hat, which is the estimated standard deviation. So when we don't know the underlying variance of a normally distributed random variable, and we have to replace that with an estimated value, we use a t-distribution instead of a normal distribution. The t-distribution looks a lot like the normal distribution, but it has somewhat thicker tails. However, it will asymptotically converge to a normal distribution as the number of observations tend towards infinity, because the estimator for sigma turns out to be consistent and converges to a normal distribution as n tends towards infinity. The f-distribution is used when we take the ratio of one chi-squared variate divided by its degrees of freedom to another chi-squared variate divided by its degrees of freedom. So in this example here, the f-statistic might be equal to x over m, where x is one chi-squared variate with m degrees of freedom, to y, which is another chi-squared variate divided by its degrees of freedom, and that's distributed as an f-distribution with m and n degrees of freedom respectively. We refer to m as the numerator degrees of freedom and n as the denominator degrees of freedom. The f-distribution, again, looks sort of like a normal distribution, except it's a bit skewed. However, as m or n or both tends towards infinity, the f-distribution will also converge to a normal distribution.